Hi, I'm Dr. Harsa. Let's proceed with Chapter 1, Introduction to Signals and Systems. Well, as the title of the course suggests, there are two main parts of this course, which are the signals and then we have the systems. First, you learn about signal classification and representation. You learn how we represent a signal and what are the different classification of signals. You learn the basic signal types, which signal types are the models and some basic operations of signals. Then you learn about sampling theory. Since in this course you learn the continuous and discrete time, so you learn how to sample a continuous time signal to get the discrete time signals. Okay, as for the analysis part, you learn how to use, about the Fourier series and Fourier transform. So you see how to get the Fourier series of signals, and then how to get the Fourier transform and some applications of Fourier transform. As for the systems, you learn about continuous time and discrete time, linear time invariant system. You'll analyze the systems in the time and frequency domain. You'll see what is the output of a system when we apply an input and impulse function as the input. That is the impulse response of a system. Yeah. Then you also learn the stability criteria for systems. In this course, actually for systems, you'll have to know about Laplace transform and Z transform. Those are considered as tools to manipulate systems. But then for this course, if we look in overall, in chapters 1, 2, and 3, you learn about signal classification and representation. But in chapter 4 and 5 is about the linear time invariant systems. Chapter 6 and 7 is about the analysis. And in chapter 8, in this course, you learn the Z transform. For Laplace transform, you'll see that in EE 350 in your third year. And some of you will have to take EEE 354. Then you'll see again Z transform. Z transform is actually to manipulate the discrete or digital signals and systems. Yeah. So that's the overall of what signals and systems is all about. Okay, so let's proceed. So what is a signal? Signals are functions of independent variables that carry information or data. These signals are functions. If we say signals, it is actually signals can be represented using functions of independent variables. Signals are something which carry data or information. Some examples: we have telephone signals, we have electric signals. Electric signals, for example, voltages and currents in circuit. Yeah, and then we have acoustic signals, for example, audio or speech signals. And you see, electric signals and acoustic signals are functions of independent variable, which is time. Okay. And for another example is biological signal. So if we look at biological signals or natural signals. For example, we have 1D biological signal, which is the ECG, and another example of a biological signal, which is 2D, we have MRI. Okay, signals as functions. Signals can be represented uh, with different types of variables. So signals as functions, we can have continuous functions of real independent variables. We can also have real valued functions of discrete variables, and we can also have discrete functions of discrete variables. And all these functions can be in 1D, one-dimensional, or two-dimensional, or it can be more. The dimension can be more. Like for example, you see the previous slide, we have the biological signals. We have one dimension and two dimension signals. And another example could be maybe a photograph. We take photos, that is two dimension. But if we have a moving photo like in the film, then we have three dimension, where the third dimension is the time. Yeah, that signals as functions. Then let's look what is a system. Systems are the entity that process a set of signals to yield another set of signals. Okay, the entity that process some signals to produce another set of signals. Okay, a system may be made up of physical components or algorithm that computes an output from an input signal. So systems are not necessarily physical components or hardware. We can also have algorithms as systems where we have input and output. Okay, which we can apply input to the algorithm, where then the algorithm will produce output. So the whole thing is can also be considered a system. So if we see here a system, it has input and outputs. What happens in the system is that the system performs any kind of processing on input data to produce output data. Okay, we are surrounded by signals. There are so many signals around us. So when we want to capture the signals, we mathematically model it as functions. Let's say, for example, the temperature in a room. There are so many factors that affect the temperature. Temperature can be considered as signals. Yes, so there are many factors that can affect the temperature in a room. Perhaps the humidity, the air flow in the room, the amount of time the room is exposed to heat or the sun. Probably, let's say there are three factors. So the three variables affecting these signals or this function. So the variables can be these are the independent variables. Yeah. So these independent variables, it can be continuous or it can be discrete, and and any functions can have it can be one dimensional or multi-dimensional. So let's say when we want to mathematically describe a function, describe a signal. So we call it a function. So there can be the independent variables can be of continuous type or discrete type, and it can be one dimension or multi-dimension. So for this course, we will look at functions or signals with only one independent variable, which is time. Okay, the signals, we will look at both the continuous time signals and the discrete time signals. For notation, uh, we must try to standardize the notation. Yeah. So let's say, for example, we use the notation X as to represent the signals. So the signals is usually represented by a small capital. Okay, so small capital X. Then for continuous time signals, we have in bracket. Okay, in bracket we have the independent variable. So in this case is time. So we use T. So to represent time. So for continuous time signals, we have X in the bracket T. Yeah. For discrete time signals, we let's say we use X, so we have small x, but in for discrete time signals we have this hard bracket. We usually use N, and N represents the discrete value integer. N is discrete value integer. So we usually we use this notation. So let's say we have a continuous time signal Y. So we have small y, and then in bracket T. And let's say we have discrete time signals y, so we have small y in heart bracket n. Yeah. So what is it that we will be doing in this course? Okay. So in this course, we will try to model physical signals using mathematical functions, and we will try to model physical systems by using mathematical equations. And we will see what happens to the systems or the equations when we apply signals or functions to the equations. Okay, these are some examples of continuous time and discrete time physical systems. So electric systems, amplifier circuits, and so on. These are just some examples. So let's look at linear electric circuits first. So this is a simple LRC circuit. Okay, so we have here this equation, first order differential equation for this LRC circuit. So you see here, IT and VT, these are functions or signals where the independent variable is time. Okay, now if we put all these functions together, okay, the whole mathematical equation is the system. All right, so this LRC circuit is a system which consists of combinations of functions in a mathematical way, right? And it is a function of one independent variable, that is time. Same here. Okay, this is another physical system, the Newton's law. This is a second order system. So we have one function ft, and also we can also consider this xt as another function. And then the whole system, okay, is represented by this equation, the Newton's law. Now I want to introduce to you analogous systems. So let's look at these two equations, equation A and equation B. Equation A is representing a model of a simple pendulum, and equation B is representing a model of LC circuit. If we look at both these equations, they are of second order differential equation. Okay, this is a second order differential equation, and this is also a second order differential equation. So we can say that both of these equations have the same mathematical form. So, okay, analogous systems are systems that are modeled by equations of the same mathematical form. So we can say that equation A and equation B are analogous systems. So what does this mean? So if we know that we have two systems which are analogous, okay, then what it means is that if we know the characteristic of one of the system, then we can tell what are the characteristics of the other system, provided that these two systems are analogous systems. Okay, so knowing the characteristic of one system, we can tell the characteristic of the other system, provided that both of the systems are analogous systems.